Hello and welcome to this presentation on VHF propagation brought to you by the RSGB Propagation Studies Committee and written by Radcom Gigahertz Bands columnist John Worsnop, G4BAO. The PSC would also like to thank Dr. Mike Willis, G0MJW, for allowing us to use diagrams from his excellent website. I hope you find it entertaining and informative and maybe even encourage you to get on the bands above 30 MHz. Now, VHF is often seen as myth and magic, only for those chosen few who understand it. Well, in fact, there is one big myth associated with VHF propagation that we can dispel straight away, and that is that radio waves travel in straight lines. This statement might almost be true in outer space, but if the wave is passing through anything other than empty space, it is certainly not. And this myth is perpetuated by the exam syllabuses. The foundation exam syllabus 6A5 states, recall that at VHF and UHF range decreases as frequency increases, and that in general VHF and UHF waves have a range not much beyond line of sight. So range on VHF and up in general is just line of sight plus a bit, eh? Well, oh dear. In general is a bit of an understatement. That sounds really boring. And if so there's no DX on VHF, why do we bother? And if that is the case, I have to ask, why are there more than 220 current 50 MHz DXCC holders? And PSC member G4BAO tells me that he's worked 66 DXCCs by not being very active on VHF at all. He's also worked 20 DXCC entities on 1.3 GHz and 36 on 70 MHz. So it's frankly misleading and might put people off by saying that VHF is just line of sight and a bit. So something else must be going on, and that's what we're going to look at in this presentation. So as I hinted earlier, radio waves are passing through something. And that something is not nice and linear or homogeneous. So we need to look at the environment for VHF propagation. Most VHF propagation occurs in the troposphere, that is, the lower 10 kilometers or so of the Earth's atmosphere, but there are some notable exceptions. As an example, let's look first at the path profile on a typical and quite workable mid-distance VHF path of around 500 kilometers. Now the slide shows two obvious things. The bulge, caused by Earth's curvature, is huge, and the Earth is not smooth in most cases due to terrain. So now we need to delve into a bit of physics to see how it's possible to regularly work such a very non-straight line path. Now radio waves are the same as light waves, they're just low in frequency, so they are subject to refraction, reflection, diffraction and scattering, and we'll look at each of these in turn. Now most VHF propagation is a combination of all of the above, and this just makes it that much more interesting. The picture shows the signal strength variation over time on a line of sight path, i.e. one where the transmitter and receiver can see each other, such as hilltop to hilltop. And the first thing you'll notice is that the signal is not at a constant level, it fades. Something else must be going on, and that something is multipath reception, where the signal arrives at the receiver via more than one path, such as a second one via ground reflection. Those of you who remember back to school days will remember doing a physics experiment where you shone a beam of light into a glass block and measured how much it was bent by the transition from air to glass. This was to introduce the concept of refraction, or bending of light by transparent but more dense media than air. The amount of bending is governed by Snell's law, which states that the angle of incidence, θ1 in the diagram, is related to the angle of refraction, θ2, by the refractive indices n1 and n2 of the two materials. Incidentally, although named after Dutch astronomer Willebrord Snellius, who lived from 1580 to 1626, the law was first accurately described by the scientist Ibn Sal at the Baghdad court in the year 984. And in the manuscript on burning mirrors and lenses, Sal used the law to derive lens shapes that focus light with no geometric aberrations. So coming back to our wave travelling through the troposphere, typically the refractive index in the troposphere falls slowly with height, and the resulting refraction causes the radio horizon to appear to be 1.33 times further away than the geometric horizon, causing the ray to eventually orbit the Earth and travel along the Earth's curvature. Changes in this refractive index profile lead to the lift conditions we're all familiar with. Radio waves are also reflected from the ground and other conductive objects. A perfectly smooth surface will give specular reflection, where the angle of incidence and reflection, theta, are equal. In real life, the ground and objects are not smooth, so we end up with multiple diffuse reflections. The reflection coefficient for ground reflections depends principally on the dielectric constant E and the conductivity S of the ground, and these are different for vertical and horizontal polarization. The third bit of physics we need to be aware of is the principle of diffraction around and over objects. If a wave strikes an edge, some of the energy gets past and around the edge. This is what causes optical shadows to have fuzzy edges and allows radio signals to diffract over hills and buildings. This can be explained using a principle derived by the Dutch physicist Christian Huygens, although it's pronounced Huygens in the Netherlands. The Huygens principle of wavelets postulates that each point on a wavefront acts as a source of secondary spherical wavelets. The combination of these secondary wavelets produces the new wavefront in the direction of propagation. Finally, we need to be aware of the principle of scattering. A radio wave hitting a particle of a certain size related to its wavelength will be scattered from it in all directions. Rayleigh scattering or Rayleigh scattering is normal scattering of radiation by particles whose size is 1/10 or less than that of the wavelength. Scattering increases with the fourth power of the frequency, and as an everyday example of this frequency dependency, scattering of the very high frequency blue part of the sun's light causes the sky to appear blue. VHF propagation, tropospheric scatter, is the scattering of RF energy from regions of the troposphere with slightly different refractive indices. Here I've listed all the main forms of extended range propagation that you'll experience on the VHF and up bands. As we deal with each of these in turn, I hope you'll see that you can explain them all with a few bits of physics we've come across so far in this talk. Now, some form of extended beyond line of sight propagation occurs on all the bands above 50 MHz. VHF is usually referred to these conditions as flat band conditions. Typical range will be 150 to 200 kilometers, dependent very much on your equipment and your QTH. It is always possible to work these distances, and is caused by normal refraction and diffraction around the Earth and terrain. A normal troposphere has the effect of making the Earth's radius appear about 4/3 of its physical radius, so hence the line of sight is usually about 4/3 the optical line of sight. In other words, just that little bit further. This 4/3 value can increase or decrease depending upon weather conditions. It can make the Earth radius appear smaller and line of sight shorter, and this is referred to as reverse beam bending. If this 4/3 factor increases, the range's workable increase as well, and in the extreme this value can become very large, extending ranges typically out to 1500 kilometers, or in extremis, usually over the sea, even 3000 to 4000 kilometers. With the formation of temperature inversion layers, where the temperature rises with height instead of falling, ducts can form that trap radio signals and carry them huge distances, just like a waveguide or caudal hop HF propagation. Such ducts often form along the edge of high pressure systems known as anticyclones, as shown in the slide. This photo, taken at sea off the Spanish coast, shows such a duct, and it's been made visible by a trapped layer of pollution inside it. A plot of refractivity against height, known as a refractivity profile, can be taken using, for example, weather balloons, and this slide shows a normal troposphere with no inversions. This refractivity profile, taken on the day of the 10 GHz UK record, which was 1429 km QSO between GM0 USI-portable and F2CT-portable, clearly shows an inversion layer which is highlighted by a red arrow. This tephrogram plot for Castor Bay in Northern Ireland for the 27th of November 2016 at midnight also shows a classic substance inversion.
The red arrow points to the nose of the inversion, and the base of the inversion is the sharp notch just below it, where the temperature starts to increase as we head high in altitude instead of the usual decrease. That is, it is inverted. A typical feature of a good lift profile is the contrast between the very dry air above the inversion and moist air below it. The greater the moisture content, the more significant the refractive index change. You will also see a thin red line on the right-hand side of the diagram, which is the radiosonde observation or RAOB diagram indicator for the gradient of N, the modified refractive index, which suggests ducting is possible.
Now, you may have heard long-distance tropospheric propagation on 2 meters, but this is a little bit different. This is Lima Yankee 2 Whiskey Romeo in Lithuania on 23 SEMS. Another form of long-distance propagation with a similar sounding name, Tropospheric Scatter, affects the 144 MHz to 5 GHz bands. The mechanism is quite different and relies on another bit of physics, namely scattering. This mode allows 24/7 communications over ranges up to around 1,000 kilometers, depending on the equipment, but it usually requires high power and big antennas. The fact that this mode is always present makes it attractive to use by professional fixed broadband links. As we mentioned earlier, tropospheric scatter is the scattering of RF energy from regions of the troposphere with slightly different refractive index values, so it depends on the amount of non-homogeneity and turbulence in the troposphere. Remembering our physics from earlier, to produce scattering, the scatterers have to be of the size that is around 10% of the wavelength. And on the bands above 1.3 GHz, raindrops meet the criteria completely, with the best scattering occurring in the 5.7 and 10 GHz bands. Now this weather-dependent form of propagation, that's scattering from raindrops, can produce paths from around 150 to 400 kilometers, depending on the equipment and the drop size and intensity. The scattering has the effect of making SSB and CW signals sound raspy, like the example here. Another VHF DX mode uses reflections from aircraft in flight to make short QSOs on bands from 144 MHz to 10 GHz. The ranges achievable are up to 800 kilometers depending on the equipment, and the aircraft must be at the approximate midpoint of the path. Aircraft reflections have Doppler shifts, and as this waterfall diagram picture shows, you can have reflections from multiple aircraft. Meteor Scatter is another popular mode on 50 MHz to 144 MHz, with paths workable up to 2,500 kilometers depending upon your equipment. This relies on the specular reflection from ionized trails left behind from meteors showers and random meteors. Path losses are very high and increase rapidly with frequency. Much of the pioneering work was done in the 1960s and 70s using CW, but nearly all the activity nowadays uses JT modes and timed periods. Modes used are JT6M and iSCAT-B on 50 MHz and FSK441 on 70 and 144 MHz. The minimum equipment to use this mode is usually in the order of about 50 watts and a dipole for 50 MHz, 50 watts and a small beam for 70 MHz, and 100 watts and a 9-element beam for 144 MHz. Here are some examples of what a meteor burst sounds like on an SSB receiver. First, JT6M. And now let's listen to some FSK 441. The WSJT software from Joe Taylor K1JT allows you to send and receive these signals via your computer. By far the most popular DX mode on the 50 to 144 MHz bands is Sporadic E or E's. With Sporadic E, signals travel via reflection from the E layer of the ionosphere over ranges between 1,000 and 5,000 km plus. And like HF, Sporadic E can be single or double hop. It's characterized by huge signals and deep fading. Sporadic E, or E's, is mainly a summer phenomenon between April and September. But there's also a smaller E season as well in midwinter in December. And to give you a feeling for what Sporadic E sounds like, this is TF3ML in Iceland on 70 MHz.
Calling CQDX 14 meters. This is Tango Fox 3 Mike Lima. Tango Fox 3 Mike Lima. Calling CQDX 14 and listening.
One little used mode for 50, 70 or 144 MHz is ionospheric scatter that relies on the irregularities in the ionosphere. Like Meteor Scatter, it usually requires large amounts of power and big antennas to forward scatter signals from the D and E layer over ranges of 1,000 to 2,500 km. While it is present 24/7, the optimum time is usually between about 10 AM and 2 PM local time, when the sun is at its highest and D layer ionization is greatest. There are marked daily variation in the intensity of ionoscatter, and some days the mode will be completely unusable. Finally, when there is an aurora in progress, it's possible to use backscatter from the polar regions on the 50 to 432 MHz bands. The lower bands are generally much better, with 432 usually requiring an EME-capable station. The aurora is caused by coronal mass ejections and coronal holes that produce energetic particles that spiral down the Earth's field lines and ionize the polar E layer. As this is a backscatter mode, all the stations involved beam in a northerly direction. This is what it sounds like. To whet your appetite for more exotic VHF modes, this is DJ5AR in Germany, and his signals are being bounced off the International Space Station. So there we have it. VHF and above is really not just about line of sight plus a bit. The lower VHF bands can give good results with Sporadic E even if you've got a poor sight, and with 50 watts to a vertical on 6 meters, you'll probably work some summer Sporadic E DX. For the other modes, high pressure systems are generally good for VHF propagation, and high K and A indices are good for the low VHF bands, as these can indicate that there may be aurora. At VHF, it's important to carefully monitor weather forecasts and maps to predict openings. The University of Wyoming's upper air soundings and the K-index will give you an indication of what bands you should concentrate on. Summer is good for rain scatter due to the prevalence of thunderstorms, whereas spring and autumn are better for tropospheric ducting and extended tropo, with coastal sites producing very good sea ducting on the gigahertz bands. That said, at VHF and above, QTH is not everything. System design is. Sometimes quite remarkable results can be had from an apparently poor site, as long as you have good equipment and you're there on the bands at the right time. If you want to know about the chances of VHF propagation at any particular time, listen to GB2RS. The broadcast includes information on both HF and VHF and is updated weekly. So thanks for your time and enjoy this part of the VHF spectrum. It can be very rewarding and challenging, but it certainly isn't just line of sight and a bit.